So what is a neutron star? Well, basically it's an atom, except this atom is huge for an atom, but small for a star. It's kilometers wide and very, very massive. They're so dense that a teaspoon of neutron star would weigh over 6 billion tons. To get into what a neutron star really is, we first have to discuss how they're formed. Stars are like humans. They're all born in essentially the same way, and they also come in all different shapes, colors, and sizes. Unfortunately, also like humans, they all die. And there are many different ways in which this occurs. The stars that we're talking about, the type that will collapse into a neutron star, are massive. Any star with an initial mass of over 8 times that of the Sun has the potential to become a neutron star. These stars are big, and that has big consequences. Now, at any given moment, a star, large or small, is maintaining a delicate balance between the gravity crushing in on it and the outward pressure generated by fusing hydrogen into helium, nuclear fusion. This can't go on forever, of course, and eventually one of two things will happen first if the star is to go on burning. The first thing that could happen is that the electron degeneracy pressure becomes high enough to counteract gravity. Electron degeneracy pressure is the pressure arising from the electrons in the star being packed elbow to elbow, unable to be packed any tighter. As you could guess, this compacting of electrons produces immense amounts of pressure, in the same way compressing a gas produces pressure. The second thing that could initially occur, which is what happens in the massive stars we're concerned with, is that the core of the star becomes hot enough to start fusing helium into other elements to keep up the outward pressure from nuclear fusion. Helium will then fuse into carbon, and eventually the star will get hotter and heavier elements will be fused, a process called nucleosynthesis, until silicon fuses into iron-56, resulting in an onion of a star, so called because it has many different shells of many different elements. Iron's heavy and difficult to fuse into other elements, so the above process accumulates iron at the core of the star. The mass of the star's core could exceed what's called the Chandrasekhar limit, approximately 1.39 solar masses. Remember the electron degeneracy pressure we mentioned earlier? It, along with nuclear fusion pressure, is what's been mainly counteracting gravity's immense crushing power thus far. But now the star's core mass is too great, and the electron degeneracy pressure is no longer sufficient in supporting the star's weight against gravity. The core of the star collapses in on itself in a magnificent catastrophic explosion. While the star's envelope turns into a supernova, the core contracts. Temperatures are so high that protons and electrons fuse to form neutrons. When the neutrons reach a certain density, degeneracy pressure, but of neutrons, not electrons, stops the core from contracting further, and the neutron star has been formed. It's incredibly tiny. The star that collapsed to form it was anywhere from 10 to 29 solar masses in size, but the largest neutron stars don't exceed 3 solar masses, or else they themselves will collapse to form black holes. An average neutron star can fit comfortably inside the borders of Philadelphia. Neutron stars also spin incredibly fast. The fastest rotation rate for a neutron star is a whopping 716 times per second. They're also ridiculously dense, and as a result, their surface gravity is immense despite their minute size, 200 billion times stronger than that on Earth. As far as composition goes, the crust of the neutron star consists mostly of a lattice of normal ions with electrons flowing through. As you go deeper into the star, you'll find higher, increasing densities of neutrons and less electrons, until you hit the super-dense core. No one really knows what's at the core of the neutron star. Our best guess is that it's almost completely neutrons. Not all neutron stars are created equal, however. They come in lots of different flavors, depending on the properties of the parent star and the circumstances of its demise. Magnetars, for example, have incredibly strong magnetic fields, but spin slowly in comparison to other neutron stars, while pulsars emit beams of electromagnetic radiation, sometimes visible from Earth. There's a lot more to neutron stars. This was just a short introduction. Neutron stars represent one of the most mind-defying extremes of this universe, minute but violent points of light. They are beautiful, but represent the intensity and splendor that may result from destruction. They are some of the loudest and most eloquent poetry that this universe has to offer, and its endless sea of awe-inspiring lyric and prose. Thank you for listening.